This video is going to put together a few different things the students have learned the past couple months. In this video, students, we're going to learn how to write a claim evidence reasoning statement that makes a claim about the relationship among wavelength, frequency, and wave speed, and specifically about a wave traveling in two different mediums. So all three of these will be included. Part 1. What does it mean when we put an up or down arrow above the wave variables? Many students are having problems just understanding, for example, this is V, it stands for speed or velocity of the wave. And then what does it mean when we say that speed increases, speed decreases? Same thing with frequency. What does it mean when we say frequency is constant or when frequency increases? And finally, wavelength. You need to know the definition of wavelength, and then what does it mean when we say wavelength is increasing and wavelength is decreasing, for example. Some of you guys are really getting confused between frequency and wave speed. You're kind of mixing up the definitions of these two. So let's use this example of these two waves together. Which of these two waves, the top wave or the bottom wave, would you say has the higher frequency? All right, well, some of you are saying the top wave has the higher frequency, and I think you're saying that because you see these waves really close together and you're thinking that's high frequency. But if you look here, right here at the bottom, it shows you the frequency. The top wave has a frequency of 1 hertz, and the bottom wave has a frequency of 2 hertz. That means the bottom wave has twice the frequency of the top wave. So what's going on? So let's focus on frequency. Frequency, F, is in hertz. It's how fast the wave is moving up and down. It's given by the source of the wave energy. What is vibrating or moving up and down? This could be your vocal cords or a speaker vibrating. It could be a tuning fork vibrating. It can be your finger touching the surface of the water and vibrating the water and making waves. In the case of the wave on the string, frequency is given by how fast the end here is moving up and down, how fast. So look at this one up here. This one's moving up and down very slowly, up, down, up, down, up, down. The bottom one's going up, down, up, down, up, down, up, down. So the frequency is given by the source of the energy. Now, let's talk about wave speed. Wave speed is how fast the wave is moving forward. This is determined by the medium, right? The stiffer the medium, the faster the wave moves forward. The looser the medium, the slower it will move forward. So the medium could be, for example, for sound, we can have sound moving through water, we can have sound moving through air, we can have sound moving through a solid like rock. Those are different mediums. For our wave on the string, we have the same string each time, but what we're changing is down here, we're changing the tension. We're trying to see how fast like the top of this wave moves to the right. How fast they're moving this way. Okay? And what you'll see is that the crests of the bottom wave are moving much faster than the tops of these waves. You can see the difference in the speed of these two waves by just trying to see how long it takes for one of these crests to move across the top. I'm going to start counting down. Okay, ready? Go 1001, 1002, 1003, 1004, 1000. It's about 4 seconds for this top wave to move across. The bottom wave, 1001. It basically takes 1 second for the bottom wave to move, the crest to move all the way across. So the top wave is moving much slower, has a much slower wave speed because the tension is low, and the bottom wave is moving much faster across the screen because it has a high tension. Let's see if you get this frequency thing. Looking at these two waves here, the top wave or the bottom wave, which wave has the higher frequency? All right, so that was a trick question because I was trying to trick you to say that the bottom one here had the higher frequency because you see them really close together. But if you notice, down here at the bottom again is the frequency. The top wave is 1.5 hertz and the bottom wave is 1.5 hertz. They both have the exact same frequency. So if I was going to write frequency on this, I would say going from here to there, the frequency is constant. That's what that arrow means. It means it's staying the same between the two. It's not going up or down. It's staying 1.5 hertz. If you got confused by that, it's probably because they're going different speeds, right? This top wave is going faster forward, and this one's going slower forward. So that makes the waves change their shape. So even though they're the same frequency, their speed is changing. Let's try some more. Wave A and wave B. I'm going to ask you to compare the frequencies, the speeds, and the wavelengths right now. The big idea is this. Some of you guys were doing the same thing on your quiz. You would look at a picture like this and you would say that this had a higher frequency by the picture, but you can't tell. There's not enough information. And some of you would say that this wave is moving faster because there's no speed information on here either. There is wavelength information though. You know you can see the wavelength, right? From here to there, that's the wavelength. From trough to trough, that's the wavelength. So you can compare the wavelengths like this. Okay, you can tell that the bottom waves are a little bit shorter than the top waves. Top waves are longer and the bottom waves are shorter. So the wavelength you can tell, but the frequency and the speed, there's not enough information. We need the waves to actually be moving to do that. What we're going to do right now is just concentrate on frequency. I'm going to make these waves move, and when they're moving you're going to be able to figure out the frequency of both of them, and then so figure out which one's the high frequency, which one's a low frequency, and then compare them when you go from here to there. Once you figure out the high frequency and low frequency, figure out are we going to put an up arrow for frequency, a down arrow for frequency, or is it constant for frequency? All right, so what I figured out was the top wave has the higher frequency than the bottom wave because I'm counting right here. Watch this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's pretty fast. Down here, 1, 2, 3, 4. So it's slower. The bottom wave has a lower frequency and the top wave has a higher frequency. So since the top wave has a high frequency and the bottom wave has a low frequency, when we're going from the top to the bottom, the frequency is getting smaller, is going down. So we're getting a down arrow because it's a lower frequency. Let's try two more. This time we're looking at V, wave speed. So now watch the speed of the top wave and the speed of the bottom wave. Which one's the higher speed and the lower speed? And then when you go from the top one to the bottom one, you want to figure out, are we going to put an up arrow for speed? Are we going to put a down arrow for speed? Or are we going to put a constant arrow for speed? All right, what I'm noticing, I'm just watching the top of this wave, looking how slow the waves are moving to the right. And now look at the bottom wave, and this one goes pretty fast. The bottom wave is moving faster across the screen. So this is the higher speed on the bottom and the lower speed on the top, and faster on the bottom. So going from low to high, that means the speed it's speeding up. It's going faster. So I'm going to put an up arrow above velocity because it's speeding up. Or wavelength, lambda. Well, we don't need the waves actually moving for this one. Just like on your quiz, you can just look at the picture, figure out the wavelengths, and then when you go from here to there, when you go from the top one to the bottom one, is wavelength getting bigger, or is it getting smaller, or is it staying constant? So you figure it out. Look at both of those waves and compare them. All right, so I'm going to mark the wavelength here from crest to crest, trough to trough, from the beginning of one wave to the next wave. Those are all three the same. And then here, crest to crest, from beginning of one wave to the next, one wave. Now notice how all these wavelengths up here are longer than those wavelengths. So high wavelengths at the top, short wavelengths at the bottom. So they're getting shorter. When I go from the top to the bottom, they're getting smaller, they're getting shorter. So the wavelength is decreasing, getting smaller when I compare them. Part 2, cause and effect. So it's important not just what words you write, but you have to write them in the correct logical flow because, time flows in a certain direction. So what cause and effect means is that when you have something happening, like thing A happens, and then it causes thing B to happen, right? There's a flow to this. You start with thing A, and then thing A happens, and that makes thing B happen. Thing B wouldn't have happened without thing A, and it goes in this order. You just don't randomly say thing B happened and thing A happened. You have to say thing A happens, which caused thing B to happen. Or you have to say thing B happened because thing A happened. Right? There's a flow to it. Let me give you 3 quick examples of cause and effect and how you might explain it. Here's a picture. Look at this picture. What's in this picture? Football player, right? And obviously he's got something wrong with his arm. So you could write a statement about this that explains it, and it could be something like this. Here's a non-example of how to explain this. Tom can't play football, so he can't throw the ball, and he broke his arm. See? Look at that. That's very random. Now, all 3 of those things might be correct things, but they're not linked together in a logical order, right? You just kind of randomly threw these things all together. You don't show any cause and effect or linking of those. Let me show you another example. Look at this picture of this mouse and a trap. Okay, now you can explain it like this. You could be like this, but this is a non-example. The mouse died. Its head was caught in a trap, and it ate some cheese, and it was hungry. Again, all those things could have been true. Each individual thing was true, but you didn't link it together in a way that flowed and described what's happening. So you got to think about cause and effect when you write your claim evidence reasoning. So here's probably a better way to explain what happened using cause and effect in the correct flow. All right? The mouse was hungry and tried to eat some cheese that was in a trap. So the trap killed the mouse. Right? This has a flow to it. It's not just a bunch of random things thrown together in a couple sentences. It has a flow to how another way you could have done it, you could have flipped around a little bit, but used the word because. The mouse died because it was hungry and tried to get some cheese from a mouse trap. Right? So look at both these explanations. They actually have a cause and effect to them. They're not just random like this other one. Let's go back to Tom, right? A better way to say this would have been, Tom broke his arm. Now he can't throw the ball, so he can't play football. This explains what's happened. Or you could do it the same way with a because sentence. Because Tom can't play football because he broke his arm and now he can't throw the ball. Right? So these 2 are good ways to write reasoning. It has to have a flow to it. You just can't randomly throw a bunch of words together. Here is an example that's very similar to your quiz, the reasoning for your quiz. I have a wave here, and then you see the tension was medium, and then the tension was changed to high, and that changed what the wave looks like on the picture. So here is a non-example. Here's something that you're writing for your reasoning. Notice how there's lots of stuff in there, but it's all just random and doesn't have any cause and effect to it. The wave equation shows that the wave is faster, the tension is higher, and the string is stiffer, which makes longer waves. Okay, and then there's a wave equation. So the wave equation is correct in here, right? Because the wavelength got longer, just like this says, and you know it's going to be speeding up, but you just threw it all together in a big pile. And then they started off by saying the wave equation shows. The wave equation doesn't show all of this. The wave equation shows some of it, but not all of this, right? Let me show you a better way to write this using cause and effect, so you link your ideas together so they make sense. All right. So what I did was, first I did this. The tension in the string was increased, which caused it to be stiffer. Stiffer medium means that the waves will travel faster. So all of that explains that going from this wave to that wave, by making it more tension, it'll go faster. So now I know it's going faster. Now the second part is where the wave equation comes in. The wave equation shows that faster waves means longer waves, and that's why the waves are longer. So this has a flow to it. The first part of it talks about stiffness and the speed, because the stiffness gives the speed, right? That's how we get the speed right here. And then you use the wave equation. You plug in the wave equation. The wave equation explains, once it goes faster, the wave equation explains why it has longer waves. So there's 2 parts to this, and there's a flow to it. You just can't throw them all together in a random list. Finally, part 3, we're going to get down to doing some examples of claim evidence reasoning. So you should have a worksheet. If you're in my class, it has 4 examples, and we will just work through these one at a time, guide you through some of them, and some of them you will just check your answers. We're on A right now. One of these waves represents sound waves traveling through air, and the other is the same sound wave traveling through water, which represents air. And so these are the pictures of the waves we have. We have wave A, and we have wave B. Then we have the claim. The claim diagram, A or B, represents something. Okay, so the answer we're going to actually do later after we do the reasoning. So the first thing we're going to look at is the evidence. So I'm going to ask you right now, looking at the green and yellow wave A and wave B, there are 2 pieces of information that are important for us proving our case. Remember, the evidence has come right off of these pictures, directly off the pictures, or the 2 things you see off these 2 pictures that are as relevant and correct. So what I notice is the frequency for each wave is the same. That means it's going to be the same sound wave basically. And then this part here is what's called a detractor, because that just tells us the length of the actual picture, which doesn't help us. But up here, I see the wavelengths, and they go with the pictures, right? So wave A has a length of 2.8, and wave B is 12.5. So wave A has short waves, and wave B has long waves. So our evidence will look something like this. Both waves have the same frequency, and then wave A has shorter waves than wave B. So those are 2 things we're going to look at and come back to later. Now let's move on to the reasoning. So the question is asking us which of these 2 represent sound waves traveling through air. So let's focus on air. Okay, and the first thing we're talking about is the speed of sound in air. That's the thing we know about from theory. Basically, I can remember compared to water, is sound slower or faster through air? And I have to think about stiffness and looseness. So first I got to figure out if air is stiffer or looser than water, and then once I figure out if it's stiffer or looser than water, then I can figure out if it's slower or faster than water. So I know it's looser than water because, you know, your hand moves very easily through air. So air is like very thin and loose. So because it's looser, we have to remember that since it's not as stiff as water, it's going to go slower because it's harder for the energy waves to travel, the sound waves to travel through something that's loose than it is for something that's stiff. So that's our first part of our reasoning when we talk about the speed. Now we have the speed, slower, and we can put that into our wave equation. So now let's think about a wave equation. And we can just copy the wave equation right off our yellow paper. And I'm going to go back up here. Remember our evidence. They both have the same frequency, so frequency is the same. That's part of our evidence. We know that's constant. And now we just figured out through logic that air is going to have slower waves, sound waves. So speed, velocity is speed here. So slower speed in air. So now we can just solve for the wavelength, and we know how to do our arrow math. The left side equation is going down, so they're equal. So the right side also has to go down. That makes wavelength go down. Okay, so that tells us something about the wavelength. So now, what do we know about the waves, the wavelengths of these waves in air? What do they have to be? So you have to write the wave equation shows us, because that's how we know it from the wave equation, that as the speed decreases, the wavelength also decreases. So we're going to have short waves. So you can pick your answer now. Which of these 2 pictures has to be the representation for air? Right, short waves. So this one's got the shorter wave. And these are really tiny waves. They're only, remember, go crest to crest. I can't even draw them on there. They're so tiny. Or trough to trough. These are small waves. These right here, trough to trough, are like this. Okay, so these are longer waves and these are short waves. So since this is short waves, that has to be our answer. Now, you don't have to write it down here, but I'll just write it just to be complete. So air has short waves, so it's A. So now we come back up to our claim, and don't forget to fill in your claim now. Okay, we figured it out. Diagram what represents what? Diagram A right here represents air. Our question was asking about air, so there's our answer. So there's our claim, evidence, and 2 parts of our reasoning. This is a 4-point answer. Okay, here's question B. This one's also asking if one of these is through air and the other one's through water. Here's our waves, they're a little different than before. Here's our claim, we're going to write that later. So do your evidence first. What are you going to write for your evidence? So I have, again, the frequency is the same, and this time Wave A has long waves and wave B has short waves. So A has longer waves than B. That's my evidence. Now we can move on to the reasoning. There's two parts of the reasoning. The first part's going to talk about what? So now you just got to think about, we're trying to look for which one of these is in water. So thinking about water, compared the stiffness of water to air. How does stiffness compare? And then how does the speed compare? So write that. Water is stiffer than air, so the sound travels faster in water. Okay, now the second part reasoning has to have what? The wave equation. So go ahead and copy the wave equation off of your yellow paper, and then we're going to put in the stuff from our evidence. Frequency and speed. Frequency is constant and speed is going up. So now you solve for the wavelength. Left side's going up, so right side has to go up. So wavelength is getting bigger. So now you write your sentence about the water has what kind of waves, short or long waves. So the wave equation shows that the faster the waves have bigger wavelength or longer waves. So now we can pick our answer. Which one of these two has to be water in order for this part here to be true? Longer waves. So the answer is A. So you go back to the top and you write your answer. Diagram blank represents blank. A represents the water. And there's our complete answer. For question C, you can check the answer with your teacher. We're going to move on to the last question. This one's a little different because it's talking about rock versus water. Which of these two represents water when you compare it to rock? So this is a little bit different. Same process though. My evidence. What is going to be your evidence? Both frequencies are the same, 1200 hertz. This time wave A is longer than wave B. Now we go to the reasoning, but this time we're talking about water versus rock. How does the speed of waves in water compare to the speed in rock? It has something to do with the stiffness. Well, water is looser than rock. You can move your hands pretty easily through water compared to rock. So since it's looser, energy will travel slower in the water. That's our speed. Now we go on to the wave equation. So copy the wave equation and figure out the wavelength in water. So frequency is constant, and then the speed is slower. So the wavelength is what? Up or down? Down. And now you're going to write your sentence. Is that shorter or longer? And then write your sentence. The wave equation shows us that slower waves makes shorter waves. So we're looking for the shorter wave for our answer. So looking at these two, the shorter wave is B, is the shorter wave. So we write out our answer now. The claim diagram what represents what? Diagram B represents water. That means this one was the rock and this one was the water.